This instruction is on finding the reactions on a part produced by the loading conditions. We'll use the free body diagrams developed before, and the steps are to select a coordinate system, sum the force components in each direction of that coordinate system. We'll be in 2D, so there will be two directions. Then we'll sum the moments and then solve the algebra. From the free body diagram before on this L bracket, we can sum the forces in the x direction, sum the forces in the y, and sum the moments. Notice that this coordinate system is dictating the positive directions for the x and y forces, and this counterclockwise is positive, so we designate that when we start to sum the moments. And then you pick a point to sum the moments. Usually you try to pick the point that will cause these unknowns to not show up in the moment equation, just to simplify the algebra. Any force line of action that passes through your hinge point does not cause any moment. So I selected point A to sum the moments and set those equal to 0. Counterclockwise is positive, so force B times its lever arm, perpendicular lever arm, is counterclockwise, so that's positive. The 200 is clockwise, and it's 1 foot away. If you have a horizontal force, you need the vertical distance, because those have to be perpendicular. The moment is the force times the perpendicular distance. And then 100 is also clockwise. It's a vertical force, so you need the horizontal distance of 2 feet. And then you solve the algebra. For our next free body, for the cart, notice you can choose a tilted coordinate system, and for convenience that's what we're going to do. If you change the x and y and tilt it, call it x primed and y primed, so that it designates you're not working in our standard x and y direction. So you sum the forces in the x prime direction. Notice that the weight, that by the way down here, 1 kilogram times 9.81 meters per second squared is 9.81 newtons. Well, this is 1,000 kilograms, so it ends up being 9.81 kilonewtons. So that weight is vertically down, and since we've tipped our coordinate axis, then you have to do that trig to get those components. So the forces in the x prime direction are this component, which lines up in the x prime direction. So that's the sine of 30, plus this component, which is c, the unknown force c times the cosine of 45. And then in the y prime direction, we have our a, our reaction forces off of the wheel showing up, a plus b, and then the components of the 9.81 and c. And then sum the moments about a. Turns out to be fairly complex. I chose A just to get rid of one of those unknowns, and this algebra tends to get a little complex. So I chose A. To sum the moments about A, you're going to have two components of your 9.81 kilonewtons causing moment, because neither one of those pass through the hinge point A. The x component is going to be counterclockwise around A, so that's going to be, remember the x component is the sine, so you go up here and you can see that x component is the sine, and then you need the y distance from A to the point of application of that force, so that ends up being 0.6. Then the y component, the y prime component, is clockwise, and remember that's the cosine, so you go get that y component and multiply by its x distance. So its x distance is from here to here, so that's 0.5, plus b. B is counterclockwise around A, so that's positive, times its distance is 1 meter. And then we go up and get both components of C, and they're both going to be clockwise. So both of these signs are negative. The x component is going to be times the y distance, so that's from here to here, so that's 0.8. And then the y component is going to be times the x distance, which is 1.1. And then you solve the algebra. For our pulley, we're going to work in the standard XY coordinate system. Here's the free body. Sum the forces in the x, sum the forces in the y, and sum the moments about point A, choosing point A to simplify your algebra, and solve the algebra. For our frame, again, we're going to work in the XY, and we're going to have to do several different parts here. First, we'll start with the ball for the sphere. Notice that these two forces, because of the symmetry, these two forces by inspection are equal to each other. So H is equal to F, so we can write that. And when you solve this algebra, that becomes important. And you sum the forces in the y. This F is equal to H comes from summing the forces in the x. You can write that if you need to. That becomes F times the cosine of 45, and you can find that if you set F equal to H, F and H are each equal to 70.71. Then we can draw the whole object enclosed in a box like we did before, and find that A and B are each 50 pounds. And then we can draw one of these supports. And I showed you how to do that before. So we know now that this is 50 pounds. This is that cable AB. Here's that pin at C. And here is our Newton's third law reaction from the ball pushing down. And then you can sum the forces in the x, in our standard x, sum the forces in the y, and sum the moments about C. The only subtlety here is that this 50 pounds is vertical, so I need the horizontal distance here. And so that ends up being 1 foot times the cosine of 45. So you just have to make sure that when you multiply that force times distance, those are perpendicular to each other. Now notice that we do know that this force is perpendicular to that surface. That's the nature of that interaction. So that ends up being, that force times distance simply ends up being the 70 times the distance from here to here. Oh, sorry, we're summing the moments about C. From here to here. So that ends up being 1 foot. And solve the algebra. Now on this truss, notice we can draw the entire truss. We're going to work again in the standard XY coordinate system. We can draw the whole truss. Notice that AB is a two-force member, so we can show it acting at point B as a two-force member at 45 degrees. And take the entire thing. Here it is pinned to the world at E. Sum the forces in the X, Y, and then I discovered that later we're going to need this for the algebra. So get EX and EY in terms of AB, because this moment equation, this algebra tends to be a little complex. We're going to choose to sum the moments about B to knock out some of that trig. And they are, let's see, the subtle thing here is to find those distances. From this trig, you can find that this angle is 22.6 and that this is slanted 22.6 in order to make this vertical. So this angle right here from the vertical, this object, this BE, from the vertical ends up being 45.2. So it's need a little bit of trig to get those distances is what we're working on. So this is 1.3, it's the length of BE. And then those distances, those horizontal and vertical distances, are times the sine and cosine of 45.2, which is the sum of that. So we end up summing the moments about B, which we go up and get this 3 kilonewton force. It's a horizontal force, so we need the vertical distance, and it's clockwise, so that's what that is. And then our EY is a vertical force, so we need the horizontal distance, so that's that one. That's what that is. And EX is a horizontal force, so we need the vertical distance, and that's that one. And so that's what that is. And then solve the algebra. Now, we haven't analyzed any of those pins yet, so, and that tends to be what you're trying to do, is to find the forces within the members of that truss so that you can find the stresses in them. Now, in order to simplify this calculation, have a look at pin B. Pin D. It's a very specialized pin. If you draw the free body of pin D, you have DC pulling on it in tension, DE in tension, DC, DE, and BD. Notice that if you sum the forces in the in this direction, let's call it X primed or whatever, if you take this pin and sum the forces in this direction, the only thing in that direction is BD, so therefore BD has to be 0. There's nothing to balance it. You can always see those T-shaped connections, and that will always happen. So that allows us to simplify pin B. So if you draw the free body for pin B, we already know the value for AB. Here's BC coming off vertical, and here's BE coming off at that 45.2 degrees. Then you sum the forces in the X on that pin and solve it, sum the forces in the Y. Now, when you start to analyze the stresses within the material, you need the internal forces and moments to find those stresses. In order to do that, there's the names of the forces change, because now we're talking about internal forces that cause stresses. In statics, this is the way we do this, and we call it AX and AY and an amount of moment. When you go to strength of materials and start drawing the free body diagram, these forces are, P is the axial force that causes either tension or compression, stress. V is the transverse shear force that causes transverse shear in stress. And M is the internal amount of moment that is the bending moment that tends to cause bending stress. Now, once you draw the free body diagram, this is the positive sign convention when you draw those. When you draw P, it is always in tension. When you draw V, it is always across the cross section. And when you draw M, it is always in that direction. That's the standard sign convention. So, after you draw the free body diagram using that sign convention, you need to solve it for P, V, and M in order to use the strength of materials equations to find stresses. So, once you've drawn the free body, then you switch back to your standard X, Y, and moment sign convention to find those forces using statics equations. So once you do your free body diagram using the sign conventions from strength of materials, you sum the forces in the x just like you always do, sum the forces in the y, and sum the moments. I chose to sum them about point A. This right here is point A. And get that amount of moment that causes bending, and you'll calculate the stress using that value later. Now notice that if you go up to this cross-section and redo that free body diagram, it looks like this. You still get P is the same value, V is the same value, but the amount of bending moment changes because the distance is different.